think two things we wanted to do in the meeting. One was just get a quick update from everyone and then spend most of the rest of the time discussing the first of, I think, at least 3 papers that we discussed. We would get into in some detail. The first one is what we'll talk about today, which is pspnet. But before that, let's just quickly go around and see whether any updates from anyone on what they've been able to do with respect to the problem. Just for context, again, we're talking about the Sevestal steel defect challenge, and many of us have been at it for a while. And so we are kind of now beginning to look at what some of the top folks have been doing. And there's post, or not a Slack post, but a Google Drive document that I shared of all the various different papers and ideas that the top finishers have used. And some of the papers that have been mentioned are the ones we will be getting into, but there are also other techniques there. So if you want access to that, I believe I posted it on Slack as well. I'll try and post it again so you can download it and use it if as a guide. But let's quickly get a update from anybody who's made any further progress on the challenge. Mr. Bannister?
I haven't actually done any submissions this week. Yeah, like last week I was like using the Catalyst library, like with ensembling some of their segmentation models. So like this week I've just really sort of been actually trying to understand how Catalyst works, and it uses the third-party segmentation library to like bring in different segmentation models. Yeah, so I've just really sort of been going through trying to understand exactly what it does and what's available and stuff. So it does seem very powerful, especially compared to something like Fast AI, where you really only have sort of the UNet easily available. This one here gives you access to like a lot of things. The one thing I was trying though was part of Catalyst. It comes with another library called Alchemy, which it's meant to be their sort of test environment where you can run experiments and sort of see the results and stuff, but I haven't been able to get that to work, or I haven't seen anywhere where it works. I think it's like, you know, like the Jovian thing we used before, but Jovian for whatever reason doesn't work in Google Colab, so maybe Alchemy is the same problem as that. So yes, I've just been playing with that really, and then obviously reading papers about pyramid networks.
Yeah.
But yeah, so no results to report this week.
I'll just give a quick update. I did manage to get the Google bytemp loss working, and try that. This is the paper that I think I posted a link to, which modifies the softmax in order to get better results, as they say, from noise in the labels. I did get it working and it ran. In fact, Rekil asked, I think, a really good question. There are 2 temperature variables that are provided to modulate the softmax for 2 different reasons. I think handling noise close to the boundary and far away from the boundary, if I recall, and the combination of the 2, that's why it's a bytemp, T1 and a T2. And T1 is supposed to be less than 1, and then T2 is greater than 1. But the issue, I tried with fixed T1 and T2 values, much like focal loss. I thought maybe there's, you know, T1 of, I think, around 0.2, if I recall, and T2 of 4 is what I used, and that gave me. It didn't give me any better results than what I had before. It gave me slightly worse results. And so I launched a different run of T1 of 0.8, and which is almost close to 1. If T1 and T2 are both 1, that's equivalent to not doing anything with the softmax. So it's a default softmax, if you will, when T1 is equal to T2 equals 1. So I kind of wanted to try with both values close to 1. So T1 still less than 1 at 0.8 and T2 slightly greater than 1 at 1.2 or 1.5. And that strangely made me run out of this space on Kaggle, which was annoying. And so I kind of didn't make further progress. But what's even more interesting is the question that Rekil asked, which is, okay, do they give you guidance on what or how best to choose T1 or T2? And unfortunately, the paper, other than telling you how it modulates the softmax function, doesn't tell you that. And in fact, they just refer to, oh, we recommend sweeping through T1 and T2 and optimizing it as part of your overall optimization and choosing hyperparameters and so on, which is great if you work at Google, but that you can sweep from 0 to say 0 to 1 in 0.1 increments and run these experiments. But even if I were not on Kaggle and still running on Google Drive, I don't think I would want to waste all that time. So it was a good exercise in getting that loss to work, but it didn't improve my results. And unfortunately, it didn't give me good guidance on what values to use either for those two temperature parameters. Anybody else, Mehul, recall anything on just the problem before we get into the pspnet paper?
Nothing on my side. Yeah, I've been just trying to get pspnet running on FastAI2. Haven't succeeded yet.
Anybody else want to say anything about the problem challenge itself before we get into the pspnet discussions?
Is Mehul going to tell us about his other competition?
I can. You want to hear a sob? You want to hear a sob story?
Yeah, if you're not crying.
No, I don't. I think it's, at least I saw it was good. Somebody started a thread on like, cry here if you didn't pick your best submission, and I think it's so that there were like many people, like even
so sorry, Mehul, for those who haven't been or who are on the call who haven't been following, maybe you want to set the context of what the particular challenge on Kaggle was, or I mean, not the details of the challenge as much as what you're talking about,
okay,
and
sure.
why it's relevant to it, because it's an important point of what we try to do with any of these challenges. So we may want to give the context.
Sure. So this is it's a biomedical image classification. It was a biomedical image classification Kaggle competition. It's from the domain of pathology. They're looking at slides of some cancer cells, and it's prostate. Yeah, it was prostate cancer. So the problem was, like, you make multiple submissions. So I made about 30, I think, and then the question is how do you, when you you have to pick 2 for your final submissions, and so you initially like right now we are working on close competitions, but when you pick 2, only the public leaderboard is you only see your public leaderboard score, and when the competition is over, you see what how well the solutions you picked would have done on the private leaderboard. And it's turning out more and more, and I think this is a very common problem. Like, even there were a couple of Kaggle grandmasters in that thread, who didn't pick their submissions that would have scored the best on the private thread, or on the private leaderboard. So for example, in the public I was around 70, and on the private I fell down to 485. But there were like other people who fell like the same thing, like falling 500 points, 500 places on the leaderboard. One of the other Kaggle, but there were teams who were able to be, who were resilient to the shakeup. And some of the more experienced Kagglers were saying, like most competitions, it's not so bad. They were complaining about the test private data set was only 500 images, and they were complaining about the metric, though I don't know why it was a new metric. So they were complaining about the size of the data set and the metric, but I think it's but then one other Kaggle grandmaster jumped in on the thread, and he said like it's good to learn it's good to try to figure out how to pick the most robust model. And I don't know, so maybe one or two of them gave some suggestions, so maybe in the future we could look at that.
Yeah, I think that is the point I wanted to focus on, which is, I think at least, it would be good if after they post some suggestions, if we can summarize and bring to a subsequent discussion. I'll schedule it. We'll talk offline and schedule it, because to me, so far from, and obviously I'm sure there are papers written on it, but at least as I mentioned, even in the chat and posted on Slack, my experience is whatever the Andrewing's machine learning, to me, that seems to come closest to addressing even the problem, which is the problem of how similar is your validation set to your test set. And in this case, I'm equating the public leaderboard to the validation set and the private leaderboard to your test set, right? And to the extent that those distributions are completely different, then it's likely that you'll see the result that you saw, because what performs well on your validation set, it seems does not, or most models that perform well on the validation set do not perform equally well, or in fact perform badly, and therefore generalize poorly to the test set. And now, to your point, it can also be argued, and I think Rekil made the point somewhere else in the thread, which is, if you are the competition, if you're hosting the competition, then how well did the competition host provide a public leaderboard and ensure that the public leaderboard is representative sample of the private leaderboard? Because if it is not, then you will see the results that just happened. And the question is, if they are after, let's say, even in our Severstal Steel Challenge, if the competition host really wanted the results from whatever models we generate to be most useful to them, then doing what just happened, meaning the validation distribution being, or the public leaderboard distribution being so different from the private distribution, can lead to problems, right? Because basically, at the end of the day, I would assume that the combination of public and private leaderboard distributions is what they would want the overall model to perform best on. And to the extent that the public leaderboard is not representative, or is in fact inversely representative, quote unquote, then it will lead to exactly the kind of problems that you say. And the lesson that at least Andrew Ng gets into is, if you are designing your own machine learning system, then, and he uses, in fact, the example of images on the web versus images on the phone to drive the point home, that if your private leaderboard is actually images on the phone, and if your public leaderboard is web images, then something that performs, and you come up with a model that performs excellent on web images, but then when you deploy it, you're actually looking for it to perform well on cell phone images, which assuming they are not of the same resolution and have other artifacts and stuff, then you're not going to get the results you expect. So he dives into, in those instances, what do you try to, or what are the actions you can take in order to ensure that your own choice of public leaderboard equivalent, that is your validation data set, distribution is similar to your private leaderboard or your test set distributions. And I thought that was very useful in this context.
Yeah,
I think part of the problem is in these Kaggle competitions, especially, I presume that you like ensembled models at the end, and I think part of the problem is basically every single model gets closer and closer to actually sort of overfitting on the public leaderboard, and then when you ensemble them together, they become even more sort of overfit on the public leaderboard. Like I've had this problem before where I was getting higher and higher up the public leaderboard by just sticking more and more models together in like an ensemble, and then when the private thing comes out, because you've overfit the public leaderboard so much, it doesn't recognize or it can't generalize on the private leaderboard. So it's not so much, I don't think, that the private leaderboard images are any different from the public ones. It's just your ensemble model is so closely tied to the public leaderboard that you've completely overfitted on it.
That's a key problem. That what you mentioned is a key problem too. But I think the reason for this dramatic movements that Mehul is talking about would be a combination of what you said and also the distribution being different would be my guess, because in all cases there is some shuffling going on, but it is not as dramatic as what Mehul mentioned.
Yeah, like in this case here, I'd started in this competition, but like I'd only made a few submissions, and so like the model that I'd put in, it was only like trained on one model. It wasn't like any ensemble, and because of the fact that everybody else fell down so much, I think like I shot away up, so I went up 175 places. But it's because my model could generalize, probably because it was only trained on one model as opposed to being trained on 50 models.
No, I had 5 submissions. Like I had 3 submissions that would have put me in the top 50. Like I had good submissions, but I just didn't select them.
I suppose you just picked your submissions with the highest public leaderboard score,
Yeah, I picked one. I tried to put I picked the highest public, and I think that is definitely some overtraining. And then I picked one with which was lower down, which was, but I didn't.
You didn't pick the right one.
Yeah, it's just maybe next time I'll prepare. I'll just look at the summaries of what the others are saying, and I ensembled maybe like 2 models.
How many? Sorry.
Like around 2 or 3 at most. No, not too many. Like I didn't have time, so I just did.
All right, that's not too many. The last competition I was in, I ensembled about 30 models together.
Oh, wow.
Like, it just fell down massively when it came to the private score.
Okay.
That's where to your point, Steve, I think the point you're making is also valid, which is when A, it's overfitting, and B, if the models are correlated, then that tends to actually worsen the ensemble. Whereas if they are very different and they aren't, then it actually helps you generalize better. Okay. Thanks, Mehul, for that. And we'll, if you can provide whatever summary learning of the masters and what they are discussing and what could be potential ways to address the problem, then that would be great.
One thing I found was some people figured out how to use the Kaggle TPUs, and they were all saying they could have much higher batch sizes. So like my batch size was 2, but for the same, the image was 256, and for the same image size on the TPU, he had a batch size of 64. So I was like, what the hell?
Could they use Kaggle TPUs with PyTorch though? I didn't think PyTorch could use TPUs.
I will look at that.
By the way, on that note, either in the general Slack or somewhere else, I saw somebody post some notebook and talk about Kaggle itself showing how their TPUs could be used. So I have it bookmarked to say, go back and look at that. So that would be an interesting thing to look at. But I don't know the answers, Steve, to what you're raising, which is the PyTorch work with TPUs.
Yeah, at the start of the competition, because I kept running out of GPU time with PyTorch, I looked into it and tried to use TPUs, and it was like saying you can't use them. Maybe it's changed now.
I see.
Certainly
Yeah,
at the start, people were using TensorFlow with TPUs, but not PyTorch.
That would make sense to me because obviously TensorFlow, Google, TPU, Google, PyTorch, Facebook. So they won't make it easy. So
PyTorch has PyTorch XLA now. It's been there for a while, so I think you can use.
All right, because this was the start of that competition, which was what, 3 months ago. So yeah, definitely then the people that in the discussion said that you couldn't, but maybe it's changed in the last couple of months.
Okay. Sorry, you were saying it is fixed now to where it can be used?
Yeah, from what I know, yes, you can use. I've seen a couple of notebooks that use it. In fact, FastAI also has a thread which is running where they're trying to move FastAI also to the ability to use TPUs. So
cool.
PyTorch itself, yeah, I think that problem is solved. I don't know specifically about Kaggle though.
Okay, but it's something to explore. That'd be good if it can.
Yeah, absolutely. Like your batch size and using larger models and all that becomes so much more easier.
Sounds good. Okay. You want to let's dive into the pspnet discussion. So should I open up the paper and then just go through it, or how do you want to best
I think let's do that.
Sorry?
Yeah, if you open up the paper and then we
okay,
can start looking
let me do that. I have it on Google Drive. Okay, can you folks see it?
Yep.
Okay, so I had shared or just posted this with some comments of my own, and I spent a little bit more time yesterday, so I was able to look at it some more and answer my own questions. But let's just go through this page by page and bring up any questions that I'm not going to read through it as much as maybe point to certain things. I think the introduction is that they're kind of giving different methods, and they've had earlier version of this paper itself, I believe, and this is, if you will, the actual final implementation of their ideas, and eventually called pspnet. And I think in related work, they talk about at least the next paper that we would want to review, which is the Deep Lab version 3+ paper. And one of the things I think at least I like about the paper is it talks about kind of the motivations, if you will, of why or the problems that solutions provided thus far have had. And that's what they cover in the important observations part of the paper 3.1. And the key, as with UNet, is the fact, eventually what they're trying to address is the fact that it when images of full size, then you have the full image available, but as you encode, the size of the image shrinks, and so you don't have the context that you have when you are looking at the full image if you will, after you've gone through the convolutional layers, and the entire attempt or the goal of whether it's UNet or this paper is to bring in awareness of the context so that you can choose and classify the pixels into the appropriate classes.
Quick
Here's the
question,
image.
Srinivas.
Sorry, go ahead.
A quick question there. So I quickly skimmed through the paper, and so there is no mention of UNet in this, right? We're not comparing it with a UNet, or it's mainly with fully convolutional networks that we're trying to compare this, right? Or was there a mention where they've kind of say that this is at least outpowered UNet or better than the UNet?
No, I did not see. In fact, I was thinking to no. The short answer is no. They do not compare to UNet.
Okay.
And in fact, even more frustratingly, in this paper or in the Deep Lab V3 paper, the convention. Well, in this paper they don't show the encoding decoding part, but in Deep Lab V3, for example. And it's annoying, and I can totally relate to why Jeremy gets extremely frustrated with this. Is UNet has the U-shaped, and in this paper and Deep Lab, it's flipped on its head, so it's like a V-shaped.
Oh, right.
So encoding you go up, and decoding you come down, and in UNet encoding you go down, and decoding you go up, which is you have to flip it on its head. But yeah, no, the short answer is no, they don't compare it. They only compare it to other kind of state-of-the-art result providing networks. They don't
Is it
prior
the
work.
fact, does this pspnet, was it out before UNet? Is that why?
No, I believe this is more recent because
UNet is older.
Yeah, UNet is older by at least a couple of years. I thought it was 16, 17 UNet.
Yeah, I mean, now when we read it, at least for me, the main problem was I was always continuously thinking versus UNet, and then as you read through and look at the architecture, you're like, wait, UNet does the same thing. So that's why I was just double checking that this is FCN is the most inefficient for doing this, I guess, at this point of time. So I mean, it makes sense that they're making a comparison with that and saying it performs better.
Yeah.
I was just wondering, like the fact that they didn't mention UNet, and like UNet is obviously sort of the default sort of segmentation model, isn't it? Plus, as well, in this one here, in their model, I read somewhere else that basically their model doesn't do the decoder part of the operation. It takes it as far as like down to the sort of the end feature maps. But if you actually want to implement this, there's another site which shows like the implementation of this, and it takes it that far, and then it says, okay, and then now for the decoder, we need to stick on the same decoder as UNet uses.
Yeah, that's correct. That's that's where I ended up, although I haven't looked at the code for implementation, which maybe Rekil can talk to us about a little more. And, I haven't dived in, or I haven't started to look at the specific code. I just wanted to go through the paper so I can get an understanding of the concepts and then look at the code to see how. But to your point, Steve, yes, that's correct. In fact, another Medium article that I'll go to once we're quickly through the paper points out the shortcoming that you mentioned, which is they don't have the decoder on the other side, and that leads to fairly poor performance, I believe, eventually.
Right.
So
they expect like an 8. I mean, there's an 8x upsampling that they do, but like Steve said, you can actually stick in a UNet decoder on that side, and that gives much better results.
Right. Yep. So here are some of the comments that I started to stick in more from my own. And if somebody knows the answer and can quickly explain, please feel free to jump in. So the pyramid pooling is the big idea that, I mean, there are 3 or 4 big ideas in this paper. One of them is the pyramid pooling part, which is a different way of combining the context information than what, somewhat similar, but still different than how UNet does it. And here they talk about the receptive field and the fact that, the receptive field of ResNet is larger than the input, but the empirical receptive field is smaller. And I didn't quite get why or what or why the empirical receptive field is less, even though the theoretical receptive field is bigger. So I just made a comment to myself saying, yeah, need to dig into that if I care and if it's important, but I don't know that it is greatly important to the rest of the paper.
Well, the pyramid pooling, yeah, so like in one of the references, it references another thing called spatial pyramid pooling, which I presume is the same thing. Yeah, because like, like in your normal ResNet or whatever, the size of your input image is restricted to whatever it is, say 256 by 256, and it's not because of the CNN having a problem, because like the CNN obviously has got its sliding window that could effectively go onto like any image size, but it's because of the fact that like when you go through your convolution layers, eventually you reach the fully connected layer, and it's expecting a certain number of inputs. And so yeah, the spatial pyramid pooling layer, it allows you to use any size input image by doing what they do here, where they have like the pyramid thing, which effectively takes the output of the conv layers and then puts it like into a set of bins just by sort of dividing the image up rather than sort of say it's got to be a specific size. And so I was wondering, is this bit refer to that, in the fact that like a ResNet, in theory, it should have been able to handle any input image, but it can't because of the fully connected layers. And so the pyramid pooling does let it handle any size image.
From what you're saying, Steve, I think that's a different problem. Conventionally, when like you used AlexNet or one of those, you ended up with a fully connected network in the end. So that, like you said, that was the limitation why you always used to start fixed size image. You couldn't do any size image. And the solution for that was basically nowadays what we do at the end of the network is you don't have a fully connected network. You actually stick in one of those average poolings or max poolings or min pooling. So irrespective of what size you start with, you can always do that min pool towards the end, or average pool or whatever, and you'd still end up with, let's say, like 1024 or 1000 vector in the end. So that is the limitation of the size of the starting input image when you use a fully connected network, fully connected layer in the end, versus like one of the average poolings at the end. This, I think what they're trying to talk about is like, when you start with the image, let's say you run a 3x3 con filter, and if you think about the top left corner, you do this thing of padding, right? And theoretically, as you go to the next layer, when you again go back to the top left corner, you start actually encroaching outside that 256 by 256 image to gather information. And that's why you kind of do this reflective padding or padding it with zeros. So I understand the concept of theoretically being bigger, but I don't understand why empirically the receptive field is being smaller.
Yeah, so that's why, but as it turns out, I mean, it's good to get to the bottom of that, but I don't think it's material to the rest of the paper, but I just didn't get it. So I marked.
Yeah, that's a good point though, yeah.
So you're explaining why the receptive field of ResNet is larger than the input image. That's because you had to pad it, right?
Not just because of the padding. So if you look at what happens is you would do the convolution, and then when you go to the next layer, it's going to become smaller, right? Your image, because of convolution. I'm assuming you're not doing like same size padding and all that stuff.
Yeah.
Conventionally, it would become smaller. Now, again, when you go and you try to convolve the top left pixel, when you stick your 3x3 on that, you start looking outside that 256 by 256 range. So that is why the the theoretical receptive field is bigger than what the image size is.
Yeah.
But I don't know why empirically it is smaller. That part,
that's the part. Yeah, I can understand I can understand what you're saying about, as it shrinks, in order to keep the 3x3 and stuff, you have to pad, and the padding says it's larger than the input image just because you're padding. But didn't understand the second part, that empirical is much smaller than the theoretical one. So
there is one mention where Jeremy mentions, I think it's with the 2017 or 2018 course, when he talks about in part 2 the SSD object detection. And there he actually goes ahead and he makes a diagram where you start seeing that if you start looking at the pixels, it's when you hit a convolution on one pixel, the contribution of all the 9 pixels is not the same, right?
Yes. That, in fact, part of this dilated convolution and stuff is,
right,
in fact, to address that.
Exactly. So I don't know if it's because of that they're saying that empirically weight is
so,
not
and he has
strong.
given a reference. So I said, well, let me go read 13 and 42, but it's somewhat orthogonal to the problem we are dealing with. So let's keep moving on.
And just goes down the rabbit hole forever.
Right, exactly. Because, with this paper itself is hard enough, even on the major areas and the implementation. So I said, forget it. I'm not chasing that. It's just bookmark for future.
Right.
So isn't the reason why the receptive field is smaller than the theoretical one, isn't that because the edge pixels don't really fully contribute because you have to pad them, so they're not really, so when you slide the convolution over the edge pixels, you're not getting full information because you're mixing it up with a bunch of garbage from the zeros. Isn't that why the empirical receptive field is smaller than the theoretical one?
But,
I mean, the theoretical one, I guess, would be the size of the image itself. But because you have to zero pad around all the edges, the actual receptive field is smaller.
No, but if you look at the section, it says that theoretically it's larger than the image. Which makes sense because, like we said, that as you keep going up.
Yeah. Theoretically, it's larger because you're padding, right? And so you might think, oh, I have a big image to start with, so I have a big receptive field. But in fact, the only pixels that really fully count are the ones that are fully inside the convolution. You know what I mean? That they don't overlap any of the 0 pixels.
I get what you're saying, but at the same time, like if you talk about the 256 by 256 image itself, there, other than, I mean, as you start going from the edge to the center of the image, this problem becomes lesser and lesser and lesser, right? Even though you make your image smaller. So at least I couldn't understand why they would be kind of mentioning that. But anyway, like I think we're going off on a tangent here.
So let's get back to the paper. So to further reduce, and then the next one that I thought was bottom line, this is one of the key ideas. We propose a hierarchical global prior containing information with different scales and varying among different subregions. So that is the big deal, which is and that kind of talks to this image here, which I'll spend a little bit of time on because that's one of the key concepts, or the key concept, if you will, the biggest one. You take the image, you do the stem thing, which is, I think, dividing it by 1 by 8, if I'm not mistaken, and stuff, and you get the feature map. Then what you do is you take through a convolution, you divide it into 4 kind of, this pyramid pooling concept is you take 4 scales. In this case, therefore, n is 4, or they have chosen that's not, you don't have to stick with 4, you can choose 6, 8, or other numbers, I believe. And let's stick with the example of n is equal to 4. Then one of them is a 1 by 1. The next one, which is the red one. The next orange scale is a 2 by 2. The blue scale is a 3 by 3. And the green one is a 6 by 6. So you kind of split this feature map into these 4 different, or not split, but you use 4 different scales on this feature map. And then subsequently do where they have this convolution that I'm pointing to, you do a 1 by 1 con to get the Z dimension. And that was the part that I didn't get the first time around, but get the Z, if you will, which is the Z dimension of all of these 4 to be the same. And then you upsample them to the same H by W size as this feature map. And then you stack them all together, or concatenate them together. This is pyramid pooling. And that's the big stuff that they talk about. So that's what they explain in the next paragraph. The pyramid module, pyramid pooling for the global scene, which is this whole scene right after a convolution by the stem.
So that part, from my understanding, was instead of like if you were to run a ResNet, instead of going all the way down to like a 1 by 1,000, I mean 1 by 1 by 1,000, you kind of stop somewhere in between where you have like a decent enough size. That's what my understanding of that feature map was.
Yeah,
Is
no,
that
in
right?
fact, I think, no, the feature map here, I believe, Rekil, is the, somewhere in the paper they talk about, they just use the stem, which is like, take it, pass it through a basic CNN to get to 1 by 8 of this size. And that's the feature map they then use to get the pyramid pooling implemented.
Okay. So because you see a right, and you see a number of channels, right, in that diagram. This is just going off by the diagram. You can see that there's like a Z-ish dimension to that. It's a cuboid, right?
Yes,
so
it's a cuboid.
Start, let's say 5112 by 5112. You'd probably stop somewhere like 36 by 36 by 256 channels. Let's say.
Yes,
You're talking of, right?
That is true. Yes, yes. So as mentioned, the courses level highlighted in the red is global pooling. It's global pooling because you have used a 1 by 1, right? So you're pooling across the entire feature map at this stage, at this level, if you will. That's why it's a global pool, right? Because it's a pooling, and they do average pooling and max pooling, and they compare the results, and they show average pooling results and gives them better results than max pool. So you just average pool across the entire feature map. That's why it's a 1 by 1 there. Then that's the courses level to generate the single bin. Then there are different levels of the pyramid pooling module with varied sizes. And those are the 2 by 2, 3 by 3, 6 by 6 that I talked about. And this is the part where I was originally confused. It's just the words threw me, and I'll try and explain what I understood them to mean, and correct me if I'm wrong, anyone. So it says to maintain the weight of the global feature, we use 1 by 1 convolutional layer after each pyramid level. So after each of these levels, they do a 1 by 1 convol. And my recollection from way back of what 1 by 1 convols are used for is basically to change the filter dimension. And I thought that was not going on here, but that's actually what is going on here. So if you can see, the filter dimension here is much larger for each of these. As Rekil pointed out, these are cuboids, which a Z dimension, meaning the H and W are along these two dimensions, the top and vertical.
Where you see the grids, yeah.
And then the width, then the depth, if you will, is the number of channels. And by doing a 1 by 1, they converted all of them to be the same, as you can see in this. And what they do here is, let's say you have, and I might get this slightly wrong, but in the example in the Medium post that I'll get to, we'll see that in a little bit. If, for example, your original image had 2048 channels, if you will, then what they want to, and you are using 4 pools, or you're using 4 scales. Is that the right word I'm looking for? Let me, into different subregions and forms pool for different locations. So if you have 4 subregions, which means the number of pooling that you're doing is 4, then you divide 2048 by 4 to get how much depth you want in each of these channels, so that when you concatenate them one after the other here, you get back the number of channels that you had in the original image. So if each of them, if the Z dimension, if each of these 4 is 512, then 4 times 512 is 2048, which is what you would get when you stack them one after the other here. So that's the goal of doing the one by one. But then I have a question which I don't know the answer to is, since anyway they concatenate the feature map, which is this part with the rest of it, so they're getting 2x. So if this is, let's say 512, I mean, sorry, if this is 2048, then this is 2048 as well. So why go through all the trouble of making sure that this is the same when you stack them? I don't know the answer to that question. If anyone does, enlighten us.
Yeah, I don't know if there is anything specifically mathematic about it. It's just that you're going deeper, you need more channels.
Yeah. So they just, I mean, that's what they talk about here. And the first time I didn't get that, but you know.
Yeah, I also didn't get that one by n part of it. Yeah, so yeah, that's good that you figured that out. Nice.
Yeah, so I went back. That's why sometimes you have to set these things away and go away. And when you come back, light bulbs go off.
So the part that I don't get is the last part where you have the stacked pooling channels, and now you apply some conv, it's labeled conv, the last operation there, yeah. And
yeah, we'll get to that, Joseph, in a minute.
Mm-hmm.
Yes, that's another key part to get back. And that is, in fact, the shortcoming that Steve and Raquel were talking about earlier as well, of this pspnet paper and method, compared to other things we'll discuss in the upcoming weeks. We'll get to that in a minute, hold that thought, because it's there subsequently in the paper. And by the way, one more thing I would need to point out is these, because you're taking fixed shots of the feature map, are not of the size H by W of the feature map, and that you get to by upsampling.
Sure.
So obviously this one by one, you have to upsample a tremendous amount to get to the full H by W size.
Yeah.
And one other thought that occurred to me, and of course there's a lot more coding and stuff, is I wonder if the dynamic unit that FastAI actually implements, that Raquel took us through several weeks back, does a number of improvements in the upscaling path. I forget the technique, but it does a number of,
pixel shuffle and stuff like that, right?
Yeah, pixel shuffle in particular, and then how you initialize the pixel shuffle to reduce the artifact. They do none of it, and I was just wondering, if you threw that code in here, how much more it would improve this process. But anyway,
I had a quick question about the pyramid pooling. Is it so they pick these 4 scales, right? So did they try more scales, or they just
no, they just stuck with 4.
They just stuck with 4.
They just stuck with 4. I mean, that's where the n is 4 for them, but you could potentially, I guess, increase or decrease that. And in fact, if you think about it, that's what the other thing. If you think about it, this is what is one of the key ideas, as I said. And in fact, in a unit paper, all you're doing is, by cross-connecting across, you are essentially achieving similar goal, is what I
also think the same thing.
Right?
In fact, at a lot more scales there too, right?
Right, exactly. So that's where, depending on the number of cross connections, you're actually increasing the number of scales at which you cross between the encoder and the decoder. Here, it's fixed at 4.
I see. Yeah, this pyramid just reminded me of something. So there are like 2 techniques that used to be very popular before deep learning. One is this idea of called Laplacian pyramids.
Laplacian pyramids, yeah.
Yeah, and then the Gaussian, and I think there's another Gaussian pyramid. A couple of so it looks like it's interesting. They borrowed ideas. That Laplacian pyramid is like very powerful, but I don't know.
Anyway,
okay, go ahead.
In fact, as you can see, I posted the first question and then I answered my own question because I figured it out yesterday. So you can see how they are talking about their pyramid pooling is a 4-level one with bin sizes of 1 by 1, 2 by 2, 3 by 3, 6 by 6. And this is the question you're asking, Mehul, of can this be more or less? And They just stick with 4, but yes, the answer is yes.
Okay, thanks.
But they haven't done anything more than that. And then, this is where, Rakel, they talk about the final feature map size is 1/8 of the input image as shown in figure 3b. So that is here.
Okay.
So you just get to 1/8 and then you do this. The second part of what they do, or another idea that they implement, and it seems totally empirical, ad hoc. Hey, it works for me, so let me do this. And I didn't spend much time at all on it, is this auxiliary loss that they add compared to the primary loss which they use. And the auxiliary loss is something that they tap off at some point in the pipeline of convolutions. And they have ablation studies which talk about how much this auxiliary loss actually during training, and they only apply the auxiliary loss during training. During inference, they just use the, I think they don't do anything with it. So if anybody has spent time on understanding the auxiliary loss and what it does, then feel free to chime in, because that's something I didn't, again, spend too much time on because it seemed totally ad hoc. They don't get into why. They just said, oh, this is a great way to train deep networks.
Doesn't Inception kind of do the same thing? Don't they have like a couple of branches dropping off and they even make predictions on that?
That's kind of what they allude to, Rakel,
Okay.
in the paper. They do refer to the Inception paper and say, yeah, they do similar things.
Okay. I mean, I'm just, now since you brought that up, it just feels like if this works here, any deep model, you should probably be having auxiliary losses while training, right?
Yeah, but I haven't seen too many people do that,
right? Exactly.
So that's why I said it seemed kind of
ad hoc, yeah,
ad hoc and like, hey, it gives me a benefit, so I'm going to stick it in here approach. And those are interesting, but
do you know if they use the same loss, or is it like a different loss that was used there versus at the end?
My recollection is it's different.
Oh, okay, interesting. Actually, I had a question going back to the 1/8, at least seems okay. There is something, but then going from 1/8, once you move over to, if you scroll back to that pyramid pooling diagram, and then you go breaking down it 1/1, 2/2, 3/3, and 6/6. That makes sense if your input image is like somewhat in the scale of like near 256, right? Then you do 1/8, you kind of drop down to like 32, and then from 32 it makes sense. It's like, okay, 1/1, 2/2, 3/3, and 6/6. But if you start like with 1024 and you break it down to 1/8, and then you're like this big void between there.
Yeah. I think, yes, that's correct. So which is why I said that, and that's a good observation or insight, which is you probably need to change these depending on the size of the image you use. But then, given that what I don't recall, I don't, we'll look at it as we go through. There are 3 data sets on which they apply this, right? So maybe those 3 data sizes are within these constraints.
Makes sense. Okay. Yeah.
But if they're not, like you're saying, then that's another good point. Then you would probably need to vary not just the number of pools and the level and the sizes at which you do them, but also how much you reduce the original feature map by as well.
Right. Okay.
Right, and whether you do the same 1, 2/2, 3/3, or you do more of these or at different resolutions. Yes, that's a good point. Okay, and then so this is what the deep supervision talks about. So see, apart from the main branch using softmax loss to train, and then another classifier is applied after the 4th stage, and they think of it as a residue block. And they back propagate both of them all the way back. Right, we let the 2 loss function pass through all previous layers. And as I said, I left it at, we'll just need to figure out how much this particular method yields. And they do talk about how much it yields on the ablation studies. We add weight to balance the auxiliary laws.
Okay.
And then they do say we abandon this auxiliary branch and only use the well-optimized master branch for final prediction. You see that here.
Right. Yeah. Oh, that's interesting. So like certain layers get trained on only one loss, and then like there are these shallow layers which get trained on both losses.
Both losses,
right?
yes.
Okay.
Yes,
Wow.
correct.
Okay.
Oops, not what I wanted to do. Be careful. Okay, where was I at? Right here. And then they get into the experiments and the ablation studies, which is very good because they provide quite a bit of detail. However, I still have questions because, and that's where I hate papers which suddenly throw in terms that they haven't defined and or talk about things which they haven't gotten into, and it just where my rant throws you off. So they iterate, and you can see my comments, 150,000, 90,000. And it's like, oh my God, you know, I can barely do, it takes 8 hours to do the Sevestal steel for 20 epochs, and they're doing 150 epochs. So obviously get big, large computers to work on. And then the other thing is the upsampling. And here is another rant, and I'll try and post links. Here they talk about dilated convolution. And there are so many, unfortunately, so many different terms that's used for upsampling. Just to rattle off some, it's dilated convolution. I've heard Jamie himself use the term transpose convolution. There's also the term deconvolve, and then there's a fractionally strided convolution. And then, as you know, Joseph pointed out, I think last week, there's this whole, I think the Google guys read too much French, the Atros convolution. And all of them are just variations of the same idea, if not the same idea.
Yeah, I thought the dilated convolution was just the same as the Atros convolution from last week.
Yeah, it is. And fractionally strided, transpose, and deconvolve are also almost the same, if not the same, except when somebody uses them and defines them in some narrower or broader way that they then use, which is
from my understanding, like the fractional and the deconvolve, aren't those all trying to make a bigger image from what you are starting? Whereas dilated and Atros are actually like downsampling, you're making it smaller. The only difference is instead of going like 3 by 3 nearby pixels, you basically introduce like a row and column of pixels in between them. So you're looking at a bigger receptive field sort of a thing, but you still end up with a smaller image. Whereas the other, what is the other one which we just, the fractional.
Yeah, you may be right. I should go back and, because the transpose convolution, my understanding
that one is upsampling. That is upsampling. Yes, that one is upsampling.
And the fractionally strided, I thought, is also upsampling.
Yes, that is also upsampling.
So that means
but this
that
is
those
not
two are upsampling and dilated and Atros are downsampling.
From my understanding, yes. I also need to double check, but from what I remember graphically, the figure, that's what it kind of does.
You're right. So dilated equal Atros equals, and both of them are for downsampling, and transpose convolution and fractionally strided convolutions are upsampling.
Yes, and deconvolve, which is again like a wrongly used term, is also upsampling. Yeah.
Correct. Yeah. So I think, I mean, the reason was I wanted to get all these terms. Similar.
I think there's a great Meetup post. Let me search for that, and then I'll share that, where someone has talked about all these possible convolutions that are there that people use, and like what you said, like millions of them which have the same.
Yeah, I wish there was a glossary, which just says, so you can, I mean, until you get all that in your head straight.
And so one more reason why I think the dilated convolution here, or why they're using, is if you start going down till you reach that feature map size, in that first part of the diagram. So if you actually use like this normal convolution, then you always go smaller, 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 right?
Correct.
So I think their strategy, from what I understood, was when you start doing this dilated convolution, you start, that's where this thing of looking at more context comes into picture. So instead of doing a 3x3, if you do a dilated 3x3, yes, exactly. You're looking at a much more bigger area than you would have been instead of looking at just 3x3 pixels.
So your receptive field is bigger.
Exactly. So that's why you're looking at context.
Okay. Yeah.
And not just that small region. Yeah, that was also some connection that I found. Yeah.
Yeah. No, that makes sense. And in fact, again, since we've gone through this before, it's in a way, that's why I was still thinking if you do hypercolumns.
Exactly.
Right. That's kind of what you're doing, right? Except you're starting for every pixel and going through all of the receptive field that it provides for that pixel back into your original image.
Right.
Right. So
I think the key breakthrough with all these things versus the old FCN, from what I understood, was like even what Mehul pointed, was doing this at different sizes.
Right. Doing it at different sizes and bringing in the context into the...
Exactly. Finally, when you kind of bring them all together, you have this context.
Right. Yeah. That's the idea. It's just how much and how differently, and then what results, and how do you keep getting better at implementing those ideas.
Yeah.
So
I have a question on this. Goes back to page 1. At the bottom of page 1 on the left side, he talks about fully convolutional network, and it seems to me that that should be fully connected network, because I've never heard of a fully convolutional network.
So those are those traditional ones that you use kind of for segmentation that they tried. So that's what we're kind of talking about now, is the idea where you kind of just convolve, and there's no idea of looking at different resolutions. And that's why like those initial networks kind of fail. And if I'm not wrong, I think Mehul, you have worked with like mask-car CNN and stuff like that. Don't they use the same thing where this concept of different resolution is not still introduced? Like where it comes to YOLO and stuff like that, whereas they start.
Yeah, in fact, if you recall, as you said, Rekil, in the object detection portion of either FastAI version 2 second part or something, he essentially talks in detail, where the set of lectures where he introduces focal laws. He talks about taking this image at different, if you will, resolution or sizes in order not to lose small objects. And it's kind of big, more and more, as you said, applied in these advanced segmentation techniques, which have to consider the high level context and bring it down to the lower resolution.
Right.
And or combine them.
Combine them together, yeah.
Yeah.
Okay, so fully convolutional is as opposed to pooling, as opposed, because both of them are fully convolutional, really. But but the pyramid pooling has convolutions at different scales that are pooled together. So that's the distinction that he's drawing, right?
Yes, exactly. Yes. So that thing where if you pull that, I mean, if you can think of that diagram, after that feature, you branch out into those 4 things, right? Yeah. That is where this is different. Whereas if it was a normal fully convoluted network, you would go from that feature map
just
to
keep
something.
Going down.
Yeah, exactly. Just smaller. Yeah, exactly.
Oh, that would be the UNet approach?
No, just the encoder side of the UNet. Like any ResNet, Inception, AlexNet, just if you look at that, you start from a big image and you basically end up something like 1 by 1 by 1024 channels. Yeah. So that is the fully convolutional network.
I see. Okay, thank you. That makes it clear.
Okay, let's see. So they go through, in this case, the study of ablation study, which is pretty good. As I was saying, they take the baseline, which is just the ResNet 50 baseline, and then do the IOU and pixel accuracy through the segmentation. And then they do max pooling, the average pooling. And then let's see what the V1 1236 is. By the way, they also do data augmentation. random mirror and random resize. And then random Gaussian blur. So they've added those aspects, and they do the dilated convolution that we discussed. And then this is the part which also concerned me. They talk about setting the batch size to 16, and then they talk about supporting batch normalization on data gathered from multiple GPUs. And that was interesting in the sense that they seem to be saying that they weren't able to hold all of this much of data in, say, a batch size of 16 was too big to hold it in a single GPU because of memory, physical memory. So they distributed it, but still kept the batch size 16 and then did the batch norm across the GPUs using an multi-processor communication technique, which is what the OpenMPI is. And that was a little bit scary / concerning, because that means in order to get equivalent results, we wouldn't be getting equivalent results, because we would be dropping unless we use TPUs, we would by necessity dropping the batch size significantly.
Yep.
Is it not just by doing it on multiple GPUs it can go a lot faster? If you spread your batch across the GPUs, you can just do it a lot quicker.
Yes, but the point I was making was they are batch norming across those independent physical GPUs.
So still to do batch norm, you still need 16 images. And for that, you have to hold these 16 images in memory, which cannot be done on one card. So they're distributing that. So
but how do you know that? Can you not keep the batch size of 16 and just do it like on one GPU?
You won't be able to hold it in memory.
You won't be able to, is what they're saying. Due to limited physical memory on GPU, we set the batch size to 16, and they then modify Caffe and make it support batch norm using the OpenMPI, which means they've actually screwed with the framework to get this to work. But I don't know.
Yeah. Then again, now this is what, 3 or 4 years old, isn't it? So
right,
the memory
yes.
is a lot bigger now.
Yep, that's true. We can try. But I just highlighted it to say, oops, something to watch out for.
Yep.
Okay, and then the annoying part is this, right? So I can understand kind of the baseline and is ResNet with the dilated network. B1 and this denote, just 1, 2, 3, 6. One is just 1 by 1, and then the 1, 2, 3, 6 is just the various sizes we saw. And then max and average is the max and average pooling. Now, what is the dimension reduction is taken after pooling mean? And what is dimension reduction? They suddenly threw this term, and I'm like, don't do this to me.
That sounds very familiar, but I can't remember what
I was with you until the time you suddenly dropped DR without defining it on me.
Reduction is taken after pooling the results. Yeah.
And I was like, dang.
What is that?
You just lost me completely on that DR stuff. So if anybody has any idea of what they're talking about, please speak up, because they completely lost me.
Yeah, not sure.
Yeah. So anyway, take a look and feel free to comment on, I was like, what? What did I miss? And I read the up to this point a couple of times, but I couldn't find explanation for it.
I was thinking it's just that making it that you break it down finely to, like, if it was on ImageNet, you would come down to 1 by 1 by 1,000, right? But why would you do that something here? Because you're trying to achieve segmentation, right? So you want to go back to your full image. So that is we can move on.
Anyway, maybe somebody will get it. Like I said, maybe if I walk away for a day or two, it might again dawn on me what they mean. But right now, I don't understand.
It doesn't mean when they apply the 1 by 1 convolutions in their
But why would they say dimension reduction? Because it's, I
Not
would,
when it takes it on from, you've got like how many channels are coming in from the first feature map, and then they reduce the dimensions, don't they, by the one by one convolution?
That's possible, but I would imagine that dimension would mean H by W and not the number of channels.
I think what Steve is saying makes sense. Yeah, that's where dimension reduction comes into picture, right? You're reducing the number of channels.
So that's what it is.
Yeah, in general terms, DR would be reducing the number of features.
Right.
But here is the channel size that we're reducing. Yeah.
Yeah. So
number of channels.
That's potentially what it means, because that at least fits what we're talking about. But it kind of is at least to me, dimension reduction typically means reducing H or W or that.
Oh, yeah. Okay. First of all, pspnet has nothing to do with segmentation the way they have drawn it, right? Isn't pspnet only like the first half of it? Or is it the whole thing where you again?
No, it's the whole. It's the whole.
Okay. It was the whole thing.
It's the whole. Yeah, it's everything. So okay, that's good. Thanks, Steve. That makes at least fits what they are saying, that DR is reducing the channel dimension. I wish they had said CR or something. But anyway, good. I understand it. Thanks. And then moving on, as I said, the ablation is good because they say average pooling is better. Also, it says that doing all these different levels or doing the pyramid with 1, 2, 3, 6 is better than just doing a 1 by 1. So instead of just global context, it's not just global context, but global context at various levels of resolution, if you will. And then they have an ablation study for Ox loss, and it doesn't seem to be so substantial. Obviously, if you're going after SOTA and state of the art and publishing your paper, maybe it matters. But I was like, okay, it seems like I can, if you're implementing, you could probably safely drop it and not suffer too much compared, for example, I don't know, they don't do an ablation study on what happens if you can't fit in images and your batch size reduces tremendously in order to do the batch norm. But so they talk about that, and then they go into the depth of ResNet and obviously show that if you use a 269, which is, I've never seen that value before with a ResNet, but if you use that, that gets them the highest score possible. And then, yeah, so you can see if they take it from a baseline of 50 to 269, it jumps, and you can see the 269 going to a very significant value. And then they do this second, no, you didn't really, thing, which is they define this multi-scale, which they don't define anywhere. And I can tell you my guess at it, but I'm not sure because they have not defined it anywhere, but I'll share what I believe it is. I think what a multi-scale, and it says MS denotes multi-scale testing. So what I think multi-scale testing means is that in the eventual tests, you test not just with the original H by W image, but you test with slices that are at the different resolutions that you have used in the pyramid pooling as well of the original image, and compare the segmentation results. That's the best explanation I could come up with, because they, again, please read through the paper and let me know if I'm totally off. Could somebody mute? Somebody's talking, or if do you have a question? Hello?
I think you have to mute them, Srinivas, because they're not listening.
I think
okay,
they're done.
That. Is that in remote control tab?
It's done.
Participants, go to participants, and then you can mute. Yeah.
I think they're muted now anyway.
Yeah, I think they're muted, yeah.
Oh, good. Okay.
Great, thanks. Okay, so MS is something somebody can figure it out post, because again they haven't defined it, and they just say that you get better results when you do multiple scale testing. Any thoughts? Has anybody read through and figured that part out?
Just from your explanation on what we just discussed right now, reducing the size to 1/8 kind of adds to what you're saying. So you like train on one thing, and then if you have a problem with like suddenly dropping it down to 1/8, so it's nice if you're testing also with different sizes. It's kind of like TTA, right?
Yeah.
It's basically that, yeah. So
Yeah,
I think it makes sense. Yeah.
That's my explanation, but it's unfortunate they don't define it anywhere. So, and then that's it. So that's, they just say, hey, finally multi-scale testing moves it to 44.94 for IOU and pixel accuracy of 81.69. So, and then using this, they came in first place in ImageNet scene parsing, and then they go over Pascal VOC 212. And to your question, that you'd asked, it'd be good to see what is the image sizes. Unfortunately, I don't know whether they provide it anywhere.
Let's see what Pascal sizes are.
So there is, they use 3 Pascal VOC 2012, which is something that I've seen Jeremy also use in the object detection thing.
Right.
And then
there's some scene passing AID.
Cityscapes is another one. Sorry?
Right. Yeah, Cityscapes is the other one. Let's check that also.
Right. And they get, even compared to the base Deep Lab network, they get better results. But then Deep Lab has gone on to Deep Lab version 3 plus, as we'll see, but at least they claim better across the board on detecting all of these individual objects or segmenting them correctly, and the mean IOU is 6 points higher as well compared to the basic Deep Lab, right, which is pretty impressive. And I think Cityscapes, Pascal VOC, and this AD20K, which seems to have a huge number of objects, if I'm not mistaken. They talk about that somewhere earlier in the paper of how it's a very tough.
Like different sizes is what they talk about, right? If I'm not wrong. Is
that
the one with the different resolutions and multiple sizes?
Oh, no, it's not images.
Oh, okay, then I'm mistaking it with something.
Scene parsing issues. So this is the one they talk about. And for example, that picture, if I'm not mistaken, is that of a boat, but you get it wrongly classified as a car. And by providing the context of the lake and stuff, you get it moved towards a boat.
Okay.
That's it. So the 3 data sets they use are AD20K, Cityscapes, and VOC 12. And can I go directly to a blog post from here, or will it?
If it's on the web, yeah, you should be able to jump.
Okay, let's see. That's different one. Where am I? I'm at a different. Oh, I'm at.
We can still see that window too.
Yeah, you're still looking at the paper, correct?
No, we can look at. So basically, I think you've shared application, Google, or whatever you're sharing. So anything you do.
Yeah, so this is, okay, so if you can see that, then let me go to, so this is a post of this guy discussing the pspnet paper. And so, need for global information, pyramid pooling, detailed ablation, blah, blah, blah. So the need, we have already kind of seen that. And Joseph, to your point here, he talks about what is an FCN and, what is the fully connected network, or actually fully convolutional network, and what that comparison is, and the issues, if you will, which motivate the pspnet, the pyramid pooling, right? And this is where he talks about the dilation. It's somewhat like the Deep Lab, and this Deep Lab is the basic Deep Lab paper, which we'll actually look at the Deep Lab version 3. I'll post the link to that if I'm not. I think I posted it already, but I'll post it again. The feature map size is 1/8 of the input image that you see here. That's where I got that this was 1/8. And then he talks about the red, orange, blue, green. Yeah, I should have caught what Steve pointed out from this discussion, where he talks about 1 by 1 for dimension reduction. I didn't catch that, but what Steve says makes a lot of sense now. Thanks, Steve. then the bilinear interpolation, then concatenating, and then you do here's where, Joseph, you had the question. It's finally followed by a convolutional layer to generate the final prediction map. So he just does the final convolution back to the original size, because you need to do that to get the per pixel classification. So that corresponds to the final convolution thing we saw here before the final prediction.
Mm-hmm.
Right? So, and then it talks about this auxiliary loss, and then the ablation study, and then the multi-scale testing, the data augmentation they do, and that, and then the comparison. So not too much different, but then it's, I guess, a real-time application of it on a data set. So, I mean, he just breaks up the paper, but I think the paper otherwise was quite well written to where it wasn't that hard to follow along. Any additional questions or comment? Maybe next week what we should do to wrap this up is maybe go through the code so we can kind of see how this is implemented.
Yep. Hopefully I should have something. Yeah.
Yeah. And I can also look at the code as is, and in fact, Steve may be able to look at it in the Catalyst,
right, in Catalyst too. Yeah.
libraries and as well.
Steve, do you have any idea if Catalyst has it implemented right out of the box like this? Where
Yeah. In fact, he has run it. That was one of his 3 ensembles that he has done.
Right. No, I'm just wondering, towards the end on the decoder side, what does that do? Does it just do a straightforward upsampling, or are they, I would imagine they're squeezing in like a decoder from UNet or something? Getting good results.
I'm not sure. I saw somewhere else there was like some other library that said they were sticking the UNet's decoder onto it.
Okay.
The one I'm using actually, it's not. I don't think it's out of Catalyst itself. It's out of that other open source.
Right.
So can you guys see my screen now?
Yep.
Okay, so this is what Steve is talking about. This was another one of explanations, and you can see here it talks about pspnet, right? Why is it an improvement? And then here you see he's just implementing the pspnet encoder contains the dilated blah blah blah, and then pyramid pooling. But here is where the problem lies, right? And in order to address it, he comes up with pspnet with UNet like decoder.
Yep.
And this is kind of what Steve is talking about.
Interesting.
In fact, I'll post this link. Rick even talks about using data AI, fast AI data bunch to kind of get that combination of pspnet with a UNet decoder.
Cool. Okay.
Right. So this is kind of what you're talking about, Steve. UNet decoder with pspnet.
Yeah, I think it's actually that paper that that article that I'd seen.
Perfect. Yeah. So yeah, hopefully next week we should be able to look at some code then.
Okay. So that's pspnet, and I'll post the links to these 2 articles, and also if we have time, and let's also begin to look at Deep Lab v3 plus, because that's the next one, and then finally we'll look at HRNet, which seems to be the state of the art for semantic segmentation, and the paper was just published in March of 2020.
Cool, sounds good.
Okay, great. Any inputs or comments from anyone else?
Nope.
Okay, thanks a lot.
Thanks, Srinivas.